For most of human history, certainty was built slowly, patiently, number by number. The universe was treated as a grand mechanism, vast, yes, but obedient. Distances could be calculated. Mass could be weighed. Time itself appeared to flow forward like a steady arrow, measurable and predictable. With every century, equations grew sharper, instruments more precise, and confidence deeper. The cosmos, it seemed, was finally yielding to understanding. But precision has a way of exposing cracks. As measurements improved, something subtle began to unravel. Independent calculations of the same universe no longer agreed. Numbers that should have converged began to drift apart. The more carefully scientists measured the expansion of space, the less consistent it appeared. Reality, when examined too closely, refused to line up with itself. The universe no longer looked like a finished structure. It appeared restless, stretching, thinning, accelerating in ways no complete equation could fully predict. Space itself seemed to be growing faster over time, as if driven by an invisible pressure embedded in the fabric of existence. The cosmos became a ledger whose totals never balanced, a map that redrew itself while the first measurements were still being made. This was not a failure of curiosity or effort. It was something more unsettling. The betrayal came from accuracy itself. Instruments built to reveal truth only deepened the mystery. Satellites mapped ancient light with exquisite detail. Telescopes measured galaxies billions of years away. Yet with every improvement, the universe appeared less familiar, less obedient to expectation. What emerged was a quiet but profound tension. The possibility that the universe, humanity learned to calculate, was only an approximation, a simplified shadow of something far more complex. A reality that behaves differently depending on when and how it is observed. And so the central question remains suspended in the dark. What if the universe that fits the equations is not the universe that truly exists? What if reality is not merely larger or older than imagined, but fundamentally stranger in its nature, its behavior, and its intent? The story of cosmic measurement begins not with certainty, but with scale. At the dawn of the 20th century, the universe was still believed to be modest in size, an island of stars contained within the Milky Way. Beyond it, many astronomers assumed there was little more than darkness. Telescopes of the era could not yet pierce far enough to challenge that assumption. Reality appeared small because vision was limited. That illusion began to fracture in the 1920s. When Edwin Hubble, working at Mount Wilson Observatory in California, turned the world's most powerful telescope toward faint. Cloud-like smudges scattered across the night sky. These objects, once thought to be nearby nebulae, revealed something extraordinary when examined closely. Embedded within them were keyfied variable stars whose intrinsic brightness oscillates in a predictable rhythm. Henrietta Leavitt had discovered years earlier that the period of this pulsation was directly related to true luminosity. By comparing intrinsic brightness to apparent brightness, distance could be calculated. For the first time, the universe offered a reliable ruler. Hubble applied this method and reached a startling conclusion. These nebulae were not clouds within the Milky Way. They were entire galaxies, vastly distant, far beyond the bounds of the known cosmos. The universe was not a single island, but an ocean filled with countless archipelagos of stars. Size itself had been misjudged. Yet Hubble's most profound discovery came not from distance alone, but from motion. By analyzing the spectra of these galaxies, he observed that their light was systematically shifted toward the red end of the spectrum. This redshift indicated motion away from the observer, a stretching of light caused by recession. The farther a galaxy lay, the faster it appeared to be moving away. The relationship was precise enough to be expressed mathematically. Space itself was expanding. This was not merely motion through space. It was the expansion of space. The universe was no longer static. It had a history. A beginning implied by reversal. Georges Lemaître, a Belgian priest and physicist, had already suggested that expansion meant the universe must once have been smaller, denser, perhaps originating from a single primordial state. What later came to be called the Big Bang began as a mathematical consequence, not an observed explosion? Measurement had opened a door to deep time. As decades passed, the task of cosmology became one of refinement. Distance measurement grew into an intricate ladder, each rung dependent on the one below it. Parallax measured nearby stars through subtle shifts in position. Cepheid variables extended that reach to nearby galaxies. Type Ia supernova stellar explosions of remarkable consistency became the next rung visible across vast cosmic distances. These standard candles burned with such uniform brightness. They offered a way to map the universe far deeper than ever before. With these tools, the universe began to take shape not only in size, but in age and structure. By the mid-20th century, competing models of cosmic origin emerged. Some proposed a universe eternal and unchanging on large scales, the steady-state model, while others supported an evolving cosmos born from a hot, dense beginning. The debate remained unresolved until chance intervened. In 1965, Arno Penzias and Robert Wilson were testing a radio antenna designed for satellite communication. No matter where they pointed it, a persistent hiss remained a uniform background noise that could not be eliminated. It did not come from Earth, nor from the Milky Way. It came from every direction at once. Unbeknownst to them, theorists had predicted such a signal decades earlier, the cooled remnant of the universe's earliest light. The cosmic microwave background was the afterglow of a universe once opaque and incandescent, released when matter and radiation first decoupled roughly 380,000 years after the Big Bang. It was ancient light, stretched by expansion into microwave wavelengths, filling all of space. Its discovery ended the steady-state debate. The universe had a beginning, and its early conditions were now observable. More than that, the cosmic microwave background was astonishingly uniform. Tiny temperature fluctuations, 1 part in 100,000, were etched across it, seeds of all future structure. Galaxies, clusters, and filaments would grow from these minute irregularities under the influence of gravity. The universe appeared comprehensible, governed by simple initial conditions evolving under known laws. By the late 20th century, cosmology entered an era of precision. Satellites like COBE, WMAP, and later Planck mapped the cosmic microwave background with increasing resolution. From these maps, scientists extracted precise values for the universe's age, composition, and geometry. The cosmos seemed to resolve into a clear inventory: ordinary matter, dark matter, and radiation shaping a vast but orderly expansion. Gravity, as described by Einstein's general relativity, was central to this picture. Matter told spacetime how to curve. Spacetime told matter how to move. In such a universe, expansion should gradually slow over time. The mutual gravitational attraction of all matter should act as a brake, pulling galaxies back toward one another, or at least reducing their outward momentum. The only question was whether gravity would eventually halt expansion, reverse it, or allow it to continue forever at a diminishing pace. This expectation was so deeply embedded that it was rarely questioned. Observations were designed to measure how much the expansion was slowing. In the 1990s, 2 independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to do precisely that. They observed distant Type Ia supernova, using them as markers to chart the universe's expansion history. These stellar explosions, visible across billions of light-years, offered a way to look back in time. The farther the supernova, the earlier the epoch it represented. What the teams found was not subtle. The supernova were dimmer than expected, not because of dust or error, but because they were farther away than predicted by a slowing expansion. The universe, it appeared, had been expanding more slowly in the past than it is now. Expansion was accelerating. The implication was immediate and profound. Some unknown influence was overpowering gravity on the largest scales, driving galaxies apart at an ever-increasing rate. This force was not localized. It did not cluster around matter. It seemed woven into space itself. The discovery was met first with skepticism, then with mounting confirmation. Independent analyses, different telescopes, alternative calibrations, all pointed to the same conclusion. In 1998, the accelerating universe was announced to the world. Within a decade, it became the dominant model of cosmology. The discoverers would later receive the Nobel Prize, but clarity did not follow. To account for the acceleration, cosmologists introduced a new component into the universe's energy budget: dark energy. The name described ignorance rather than understanding. It was not dark in the sense of invisible matter, but dark in explanation. It did not emit or absorb light. It revealed itself only through its gravitational effect, an effect that was repulsive rather than attractive. When the numbers were tallied, the result was unsettling. Ordinary matter, everything made of atoms, stars, planets, life accounted for less than 5% of the universe. Dark matter, inferred from galactic rotation and gravitational lensing, made up roughly 27%. Dark energy dominated the remainder, approximately 68% of all cosmic content. The universe humanity inhabited was no longer central, nor even typical. It was a minority component in a reality governed by forces unseen. Even more unsettling was the realization that Einstein himself had anticipated something like this. In 1917, attempting to construct a static universe, he introduced a term into his equations, the cosmological constant that acted as a repulsive force. When expansion was discovered, he reportedly called it his greatest mistake. Yet decades later, that same term resurfaced as a possible explanation for dark energy. But the numbers did not align. Quantum field theory predicted a vacuum energy density vastly larger than what was observed, off by more than 100 orders of magnitude. The universe's acceleration was real, but its cause remained profoundly mismatched with theoretical expectation. Measurement, once again, had revealed not closure, but contradiction. As cosmologists refined their tools, tension began to emerge in unexpected places. The expansion rate of the universe, the Hubble constant, could be measured in two independent ways. One relied on the early universe, using the cosmic microwave background as observed by Planck. The other relied on the late universe, using supernova and distance ladders calibrated by Kiffids. These two methods should converge on the same value. They did not. The discrepancy was small in absolute terms, but statistically significant and persistent. As measurements grew more precise, the disagreement sharpened rather than faded. The universe appeared to be expanding at different rates depending on how and when it was measured. What had once been a single, coherent expansion history now fractured into competing realities. This was not a trivial calibration error. Entire collaborations rechecked data, instruments, and assumptions. New methods were introduced: gravitational lensing, baryon acoustic oscillations, standard sirens from gravitational waves. Each new probe added detail, but not resolution. The discovery phase of cosmology, once defined by revelation, had reached an unexpected threshold. The universe was not only expanding and accelerating, it was internally inconsistent in ways that could not be easily reconciled. What began with Hubble's simple observation, that galaxies are moving away, had evolved into a deeper confrontation. The cosmos, measured with extraordinary care, was no longer agreeing with itself. Gravity alone could not explain its behavior. Matter was insufficient. Even space-time, once thought to be the stable stage on which physics played out, now appeared dynamic and unsettled. The promise of clarity that accompanied each discovery had given way to a more disquieting truth. Precision does not always lead to simplicity. Sometimes it exposes a reality that is richer, stranger, and far less obedient than expected. The universe had been measured. Into mystery, the discovery that the universe's expansion was accelerating did not arrive as a dramatic explosion of data, but as a quiet contradiction, one that cut directly against the deepest expectations of modern physics. For nearly a century, Einstein's general theory of relativity had stood as the most accurate description of gravity ever constructed. It had predicted the bending of light by massive objects, the slowing of time near strong gravitational fields, and the existence of gravitational waves long before they were observed. At its core was a simple, elegant principle: matter and energy curve spacetime, and that curvature governs motion. In such a universe, gravity is always attractive. On the largest scales, it should act as a cosmic brake. If the universe began in a hot, dense state and expanded outward, gravity generated by all matter within, it should gradually slow that expansion. The question was never whether expansion was decelerating, but by how much. Every model of 20th century cosmology was built on that assumption. Even scenarios in which expansion continued forever assumed a gradual easing. A universe coasting towards stillness, the supernova results shattered that expectation. Instead of slowing, the expansion rate was increasing. Distant galaxies were not merely drifting apart, they were being carried away faster and faster as time passed. The farther into the future the universe moved, the more rapidly space itself appeared to stretch. This was not motion through space, but the growth of space. Entire regions of the cosmos were being pulled beyond one another's reach, not by explosion or collision, but by an unseen influence embedded everywhere at once. The shock was not emotional, it was structural. The equations of general relativity still worked with exquisite precision in local environments. Planetary orbits remained stable. Stars formed and evolved as expected. Black holes behaved exactly as Einstein had predicted. On scales of laboratories, solar systems, and even galaxies, gravity obeyed every test ever devised. Yet on the largest scales of all, those same equations produced results that no longer matched. Observation, unless something entirely new was added. This was not a missing object that could be located or detected. It was a missing explanation. Earlier in the century, astronomers had faced a different kind of absence. Galaxies rotated too quickly to be held together by visible matter alone. Clusters bent light more strongly than their mass allowed. That problem had led to dark matter, an invisible form of mass that behaved gravitationally like ordinary matter, but did not emit light. Dark matter made sense within Einstein's framework. It added gravity, where gravity was missing. Accelerating expansion did the opposite. It demanded a component that counteracted gravity, not by shielding it, but by overwhelming it. Something that did not clump into stars or galaxies, something that grew more influential as space expanded. Something that exerted a negative pressure on the universe itself. Gravity pulled matter together. This new component pushed space apart. The implications were staggering. Pressure in general relativity contributes to gravity just as mass does. Ordinary pressure strengthens gravitational attraction. Negative pressure does the reverse, it produces repulsion. For expansion to accelerate, the universe had to be dominated by an energy with strong negative pressure, evenly distributed throughout all of space. This realization reframed the problem entirely. The universe was not missing matter. It was dominated by something fundamentally different from matter. Dark energy was not discovered in a laboratory. It was inferred from geometry, from the way distances, brightness, and time failed to align. Its existence was written not in particles, but in the stretching of space itself. Every cubic meter of empty space appeared to carry a small but persistent energy, exerting pressure outward in all directions. Empty. Space was not empty. The intellectual shock deepened as physicists confronted the scale of this conclusion. Calculations based on supernova data, cosmic microwave background measurements, and large-scale structure all converged on the same unsettling ratio. Roughly 2/3 of the universe's total energy content existed in this unknown form. Everything familiar, stars, planets, gas, dust, life was reduced to a trace component of reality. Even dark matter, already mysterious, was overshadowed. The universe, humanity, could see, touch. And matter was not the main actor in cosmic evolution. It was a minor detail riding atop a much deeper structure. This realization forced a profound reconsideration of what it meant to understand the universe. Physics had always progressed by identifying constituents, atoms, particles, fields, and describing their interactions. Dark energy resisted this approach. It could not be isolated, shielded, or switched off. It did not interact with light or matter in any conventional way. Its presence was inferred only through its cumulative effect on space-time. Over billions of years, equations could describe its influence, but not its nature. The tension between theory and observation became increasingly stark. Quantum field theory, the framework governing particles and forces at the smallest scales, predicted that empty space should possess vacuum energy arising from quantum fluctuations. Particles and antiparticles briefly appear and vanish, contributing energy even in a perfect vacuum. When physicists calculated this vacuum energy, the result was enormous, so large that it would have caused the universe to expand catastrophically fast, tearing itself apart in an instant. Yet the observed acceleration was gentle, almost delicate. The discrepancy between predicted vacuum energy and observed dark energy was not small. It was off by factors of 10 raised to powers exceeding 100. No other mismatch in the history of physics came close. It was not an error that could be fixed with adjustment. It was a chasm between theory and reality. The shock, then, was twofold. Observation demanded dark energy. Theory could not explain its value. At the same time, the structure of general relativity itself came under scrutiny. Einstein's equations allow for a cosmological constant, a term representing energy intrinsic to space. When Einstein first introduced it, he did so reluctantly, attempting to force a static universe. After expansion was discovered, the term seemed unnecessary. Its return now, as a dominant cosmic component, was deeply ironic. Yet even the cosmological constant explanation carried unease. If dark energy were truly constant, unchanging over time, then the universe's future was stark. Expansion would continue forever. Galaxies drifting beyond one another's horizons, stars burning out, matter thinning until only isolated remnants remained in an ever colder, darker cosmos. But if dark energy evolved, even slightly, the consequences could be far more dramatic. Some models suggested that its strength might increase over time, leading to a big rip, where galaxies, stars, planets, and eventually atoms themselves would be torn apart by runaway expansion. Others suggested it might decay, altering the universe's fate in ways not yet imagined. None of these possibilities violated current observations. All remained consistent with data. What made the shock so profound was not merely the presence of dark energy, but the way it exposed the limits of intuition. Physics had grown accustomed to invisibility. Neutrinos passed through matter unnoticed. Dark matter shaped galaxies without revealing itself. But dark energy was different. It did not hide within space. It was space. The very stage on which physics unfolded had become an active participant. This realization undermined a long-held assumption that empty space was merely a backdrop. Instead, space possessed properties, dynamics, and energy. It could stretch, accelerate, and dominate the evolution of the universe. The vacuum was no longer passive. It was powerful. The shock reverberated through every corner of cosmology. If most of reality was invisible and repulsive, what else might be missing? If space-time itself could behave in ways unanticipated, how stable were the laws assumed to govern it? Were constants truly constant? Was gravity complete? Even more unsettling was the realization that local success did not guarantee global truth. Physics worked perfectly where it could be tested directly. The failure appeared only when extrapolated to the largest possible scales. The universe obeyed the same equations everywhere, yet the outcome differed depending on scale. This suggested that understanding reality required more than assembling correct pieces. It required knowing how those pieces behaved collectively across unimaginable distances and times. The accelerating universe forced physicists to confront a possibility long resisted, that the majority of reality might be fundamentally inaccessible to direct measurement, not hidden by distance or technology, but by nature. A component that reveals itself only through the expansion of the cosmos, never through direct interaction. In this sense, the shock was philosophical as much as scientific. The universe was not obligated to be intuitive. It was not required to privilege the forms of matter capable of asking questions about it. Humanity's instruments had reached a point where they no longer revealed comfort, but strangeness. Acceleration transformed cosmology from a story of origins into a story of limits. The equations had not failed outright. They still described gravity with unmatched accuracy. What failed was the assumption that gravity and matter were the whole story. Something vast had been missing all along, shaping the universe silently from within the fabric of space. The realization settled slowly but inexorably. Most of reality was not luminous, it's not tangible, and not explainable by existing frameworks. The universe was not merely larger than expected. It was governed by principles that had never been encountered before. The shock was not that humanity had discovered something new. It was that, for the first time, precision itself had revealed how incomplete understanding truly was. The universe had spoken clearly, and what it revealed was profoundly alien. The acceleration of the universe did not end the investigation. It began at once expansion was confirmed to be speeding up. Cosmology entered a phase defined not by speculation, but by data vast, meticulous, and increasingly unforgiving. The universe would be interrogated not through single observations, but through overlapping measurements, independent instruments, and entire generations of surveys designed to test whether this strange behavior was real, consistent, and universal. The first answers came from space. Satellites such as the Wilkinson Microwave Anisotropy Probe, known as WMAP, were launched to study the faint afterglow of the Big Bang with unprecedented precision. This ancient radiation, the cosmic microwave background, carried within it a frozen image of the universe when it was only 380,000 years old. WMAP did not simply confirm its existence, it mapped its minute temperature variations across the entire sky. These variations were not random. They encoded information about the universe's geometry, its total energy content, and the relative proportions of its components. From these maps emerged a startlingly precise picture. The universe was nearly geometrically flat. Its age could be pinned to approximately 13.7 billion years, and its contents followed a ratio that defied intuition: roughly 5% ordinary matter, about 27% dark matter, and nearly 68% dark energy. Later, the European Space Agency's Planck satellite refined this picture even further. With higher resolution and greater sensitivity, Planck revealed the subtle ripples imprinted on spacetime itself, acoustic oscillations from the early universe. Frozen into the cosmic microwave background like fossilized sound waves, these ripples confirmed not only the presence of dark matter and dark energy, but their dominant role in shaping cosmic evolution. The universe, it seemed, was not merely expanding under gravity's weakening grip. It was being driven by a hidden architecture invisible to every human sense at the same time. Telescopes on Earth and in orbit were mapping the universe in 3 dimensions. Large-scale galaxy surveys such as the Sloan Digital Sky survey charted the positions of millions of galaxies across billions of light-years. What emerged was not a random scatter, but a vast cosmic web. Galaxies traced filaments stretching across immense distances, intersecting at dense clusters, while enormous void regions, nearly empty of matter, yawned between them. This structure was not decorative. It was diagnostic. The filaments and voids reflected the interplay between gravity and expansion over cosmic time. Dark matter formed the scaffolding, collapsing under its own gravity and pulling ordinary matter along with it. Dark energy worked in opposition, slowing the growth of structure by accelerating the expansion of space. The shape of the cosmic web preserved a record of this competition. Written across the largest scales the universe could offer, every new dataset reinforced the same unsettling conclusion: the universe's visible contents were a minority influence. Stars and galaxies were passengers, not drivers. Yet beneath this growing clarity, fracture was forming. The cosmic microwave background provided a snapshot of the universe's earliest measurable state. From it, cosmologists could infer how fast the universe should be expanding today, assuming the laws of physics remained consistent over time. This early universe prediction yielded a specific value for the expansion rate, the Hubble constant. Meanwhile, astronomers measuring the universe directly in the present year using Q-fied variables, type Ia supernova, and the motion of galaxies arrived at a different value. The late universe measurements consistently indicated a faster rate of expansion than the early universe predictions. At first, discrepancy was subtle, easily dismissed as experimental uncertainty. But as data improved, the gap widened. The numbers refused to converge. This growing disagreement became known as the Hubble tension. It was not a disagreement between theories, but between observations of the same universe viewed at different times. The early universe, measured through the cosmic microwave background, appeared to follow one expansion history. The late universe, measured through galaxies and supernova, followed another. The implication was deeply troubling. Either one set of measurements was flawed in ways no one could identify, or the universe itself was more complex than the standard cosmological model allowed. Physicists responded not with speculation, but with relentless scrutiny. Instruments were recalibrated. Distance ladders were rebuilt rung by rung. Kifid stars were reanalyzed with data from the Gaia satellite, which measured stellar positions and distances with extraordinary precision. Supernova light curves were corrected for every known source of bias. Independent methods were introduced to cross-check results. The tension remained gravitational. Lensing where massive objects bend the path of light offered another probe. By studying how galaxies distort the images of more distant objects, researchers could infer the distribution of mass and the growth of cosmic structure over time. These measurements, too, supported a universe whose late-time expansion appeared faster than early-time predictions. Baryon acoustic oscillations. The fossilized imprint of sound waves from the early universe provided yet another standard ruler. Once again, results reinforced the discrepancy rather than resolving it. The universe was being measured from every possible angle, and it was telling two slightly different stories. This was not a failure of technology. It was a failure of expectation. The standard model of cosmology known as lambda-CDM had been remarkably successful. It combined general relativity, dark matter, and dark energy into a coherent framework that explained the cosmic microwave background, its large-scale structure, and galaxy formation with stunning accuracy. But the Hubble tension hinted that this model might be incomplete. Something subtle, something overlooked, might be influencing cosmic expansion differently at different epochs. Possibilities multiplied. Perhaps dark energy was not constant, but evolving over time. Perhaps an unknown form of radiation influenced the early universe. Perhaps neutrinos possessed properties not yet fully understood. Perhaps gravity itself behaved differently across cosmic scales. Each hypothesis carried profound implications, and none could yet be confirmed. What made the deeper investigation so unsettling was not the presence of disagreement, but its persistence. In science, discrepancies usually fade as data improves. Here, improvement sharpened the conflict. The universe appeared to be internally inconsistent, not chaotic, but layered, revealing different behaviors depending on the depth of observation. Early universe measurements looked back to a time when matter and radiation were tightly coupled, when space was dense and hot, and when quantum fluctuations governed structure. Late universe measurements observed a cosmos diluted, cooled, and dominated by dark energy. The laws connecting these eras might not be as simple as once assumed. This raised a profound question. Was the universe governed by a single, unchanging set of rules, or did its behavior evolve along with its expansion? Even space-time itself came under renewed scrutiny. General relativity described gravity as geometry, but it assumed that geometry responded predictably to energy and matter. If dark energy evolved, or if new fields influenced expansion, then spacetime's response might be more complex than previously thought. The deeper investigation also forced cosmologists to confront the limits of inference. Most of what was being measured, dark matter, dark energy, early universe fluctuations, could not be observed directly. Their existence was reconstructed from effects, patterns, and residuals. The universe was speaking indirectly. An interpretation mattered. Every galaxy survey, every satellite map, every lensing measurement added another layer to the story. None contradicted the reality of acceleration. All confirmed that ordinary matter was insufficient. Yet together, they revealed that understanding the universe required more than cataloging its contents. It required understanding how those contents interacted across time. As data accumulated, the universe appeared less like a static object and more like a process, one whose behavior depended on its history. Expansion was not simply a rate. It was a narrative unfolding differently across epochs. The deeper investigation did not resolve the mystery. It refined it. The universe was not only stranger than expected, it was subtly inconsistent with itself in ways that resisted simplification. Precision had reached a point where small differences carried enormous significance. In this new phase of cosmology, the question was no longer whether the universe was accelerating. It was why the same universe, measured with exquisite care, seemed to tell two incompatible stories about its own expansion. The data did not accuse error. It accused incompleteness. And as instruments grew more powerful, the universe did not retreat into clarity. It leaned further into strangeness, as if inviting a deeper reckoning with the nature of reality itself. The investigation continued not toward closure, but toward a horizon where explanation itself began to bend. The disagreement did not fade with time. It sharpened, as instruments grew more precise and methods more refined. The tension at the heart of cosmology deepened into something far more troubling than a numerical mismatch. What had once appeared as a narrow gap between measurements hardened into a persistent divide. The Hubble tension was no longer a curiosity to be resolved with better calibration. It became a crisis of interpretation. The universe was being measured with extraordinary care. Space telescopes mapped ancient light to fractions of a degree. Stellar distances were recalibrated using parallax measurements, precise enough to detect motions smaller than the width of a human hair seen from kilometers away. Supernovae were cataloged across cosmic time, with corrections for dust, metallicity, and environment. Every known source of error was interrogated, modeled, and minimized. Yet the more carefully the universe was measured, the more stubbornly it refused to agree with itself. Early universe measurements, drawn from the cosmic microwave background, spoke with remarkable internal consistency. They described a young universe governed by well-understood physics radiation, matter, gravity unfolding from simple initial conditions. From that ancient snapshot, cosmologists could extrapolate forward. Predicting how fast the universe should be expanding today, late-universe measurements told a different story. Direct observations of stars, galaxies, and supernova indicated a faster expansion rate than the early universe picture allowed. These measurements were not scattered or erratic. They converged tightly just around a value that conflicted with the one inferred from the early universe. Two stories. One cosmos. At first, it was tempting to blame the messengers. Perhaps the early universe was being misinterpreted. Perhaps the cosmic microwave background carried subtle distortions not yet understood. Or perhaps the late universe was being mismeasured. Its distances stretched by hidden biases or astrophysical effects. But as new probes joined the investigation, the escape routes narrowed. Gravitational lensing added weight to the tension. By observing how massive structures bend light, physicists could trace the growth of cosmic structure over time, another indirect measure of expansion. These results align more closely with the late universe picture. So did measurements using baryon acoustic oscillations, the fossil imprints of sound waves from the early universe embedded in the distribution of galaxies. Even gravitational waves entered the conversation. When massive objects like neutron stars collide, they emit ripples in space-time that propagate across the universe. These standard sirens carry information about distance independent of traditional cosmic ladders. Early results, though still uncertain, hinted again at a faster expansion rate. Each new method was meant to arbitrate the dispute. Instead, it added to the unease. The problem no longer resembled a disagreement over technique. It resembled a disagreement over reality. If both sets of measurements were correct and all evidence suggested they might be, then the universe itself was behaving differently depending on the era being observed. The expansion rate inferred from the infant universe did not match the expansion rate measured in its maturity. This raised a deeply unsettling possibility. The laws governing cosmic evolution might not be static. For generations, physics had been built on the assumption that fundamental constants were fixed: the speed of light, the strength of gravity, the properties of particles and fields. These were thought to be timeless truths, woven into the fabric of reality itself. The Hubble tension challenged that assumption quietly but relentlessly. What if dark energy was not constant, but dynamic? What if its influence changed over cosmic time, subtly altering the expansion history in ways not captured by existing models? Such a possibility would leave early universe measurements largely intact while modifying late-universe behavior. What if new fields existed, fields that interacted weakly with matter, strongly with spacetime, emerging only after the universe cooled and expanded past a certain threshold? Such fields could accelerate expansion without leaving obvious traces in the early universe. What if gravity itself evolved? General relativity had passed every local test with extraordinary success, but it was tested primarily on scales of stars, galaxies, and solar system's tiny islands in a vast cosmic ocean. The Hubble tension raised the possibility that gravity's behavior on the largest scales might deviate slightly from Einstein's predictions. Not enough to disrupt local dynamics, enough to alter cosmic expansion over billions of years. These were not radical ideas born of desperation. They were cautious extensions of known physics, explored mathematically in peer-reviewed literature, debated across conferences and journals. Yet each carried consequences that reached far beyond cosmology. If dark energy evolved, the universe's fate was no longer fixed. Eternal acceleration might give way to slowing reversal, or something far more dramatic. If gravity changed with scale or time, the foundation of modern physics would require revision. If fundamental constants were not truly constant, then the very notion of immutable laws would dissolve. The existential unease lay not in any single hypothesis, but in what they implied collectively. The universe might not be governed by a single, unchanging rulebook. Its behavior might depend on context and scale, on epoch, on conditions that emerged only after billions of years of evolution. Reality in this view was not static. It was historical. This realization struck at the heart of scientific intuition. Physics had long sought universal descriptions, equations that applied everywhere, always. The success of such equations had fostered a quiet confidence that understanding a small part of the universe meant understanding the whole. The Hubble tension eroded that confidence. Here was a case where understanding the early universe did not guarantee understanding the late universe, where extrapolation broke down not because of ignorance, but because of genuine novelty emerging over time. The universe appeared to have phases, not unlike matter changing state from solid to liquid to gas, yet governed by deeper transitions in spacetime itself. Some theorists began to explore whether spacetime possessed its own internal degrees of freedom, capable of rearranging over cosmic time. Others considered whether the vacuum of space underwent transitions, slowly shifting its energy landscape as the universe expanded and cooled. These ideas were speculative, but not ungrounded. Quantum field theory already described vacuum states with different energies. Cosmology already invoked inflation, a brief epoch when spacetime expanded exponentially due to vacuum-like energy. The notion that something similar, though gentler, might occur later in cosmic history was not inconceivable. Yet speculation alone could not resolve the crisis. The deeper problem was epistemological. How does one test the behavior of space-time itself? How does one distinguish evolving laws from incomplete models? When observation and theory diverge, which must yield? The Hubble tension forced cosmology into a rare and uncomfortable position. The data were abundant, precise, and mutually reinforcing. The theory was elegant, successful, and deeply entrenched. Neither could be easily discarded. This standoff transformed the tension into something more profound than a parameter mismatch. It became a question about the nature of explanation. Perhaps the universe was not inconsistent. Perhaps it was layered. Early universe physics might operate under conditions so extreme, dense, hot, tightly coupled, that certain degrees of freedom were suppressed or irrelevant. As the universe expanded and cooled, new behaviors could emerge, much as collective phenomena emerge in complex systems. Superconductivity does not appear at high temperatures. Consciousness does not emerge from single neurons. New rules can arise without violating old ones. If so, then the Hubble tension was not evidence of error, but evidence of emergence. This perspective reframed the crisis. The universe was not contradicting itself. It was revealing that its behavior depended on scale and history in ways that simple extrapolation could not capture. Still, this interpretation carried a heavy philosophical weight. If the universe's large-scale behavior could change over time, then certainty itself became provisional. Laws once considered fundamental might be effective. Descriptions valid only within certain regimes. The stability of reality, the assumption that tomorrow's universe would obey the same principles as yesterday's could no longer be taken for granted. This uncertainty was not chaos. The universe did not appear arbitrary or erratic. Its behavior was consistent within epochs, coherent across structures, and mathematically describable. But coherence did not imply simplicity. The Hubble tension illuminated a universe that was internally subtle, not broken. Yet the emotional impact remained. Humanity had reached a point where increasing knowledge no longer collapsed uncertainty. It expanded it. Precision had not delivered closure. It had delivered depth. If the universe could not agree with itself across time, then understanding it required humility. It required accepting that reality might be richer than the frameworks built to describe it, and that those frameworks might evolve just as the universe does. The crisis, then, was not merely cosmological, it was existential. For centuries, science had promised convergence, a slow march toward a single, unified description of reality. The Hubble tension suggested a different future, one where understanding deepens without necessarily simplifying, where mystery is not eliminated but refined. The universe, measured with unprecedented care, was no longer offering reassurance. It was offering a challenge, and beneath that challenge lay a quiet, unsettling question if space-time itself could change its behavior across epochs. If expansion could follow different rules depending on when it was measured, then how stable was reality really? The universe was not just expanding faster. It was pulling the foundations of understanding outward with it, and the deeper the investigation went, the more it became clear. This was not a problem that could be solved by adjusting a number. It was a signal that the universe was inviting a new way of thinking about what laws are, and how reality chooses to obey them. Dark energy entered cosmology not as a solution, but as a placeholder marking ignorance with mathematical necessity. It was invoked because something had to be there. Observations demanded it. Without an additional component woven into space itself, the accelerating universe could not exist as measured. And so dark energy became the quiet centerpiece of modern cosmology, an influence everywhere, visible nowhere, defined not by what it is, but by what it does. At its simplest, dark energy is treated as a property of space. As the universe expands, more space comes into existence, and with it, more dark energy. Unlike matter, which dilutes as volume increases, dark energy appears to maintain a constant density. The result is counterintuitive but profound. The larger the universe becomes, the stronger dark energy's total influence grows. Expansion feeds acceleration. The most conservative explanation for this behavior lies within Einstein's own equations. General relativity allows for a term known as the cosmological constant, tan energy inherent to spacetime itself. When Einstein introduced it in 1917, it was an act of desperation, mathematical adjustment meant to hold the universe static. When expansion was later discovered, the term seemed unnecessary and was discarded. Its resurrection, nearly a century later, was deeply ironic. As a cosmological constant, dark energy would be perfectly uniform, unchanging across time and space. It would exert a steady negative pressure, driving eternal acceleration. This model, often called lambda CDM, fits a remarkable range of observations with astonishing accuracy. It explains the cosmic microwave background. the large-scale structure of the universe, and the distribution of galaxies with a simplicity that is difficult to abandon. And yet, it carries an unresolved tension at its core. Quantum field theory predicts that empty space should be filled with vacuum energy, arising from quantum fluctuations, pairs of particles constantly appearing and vanishing. When physicists calculate the energy density of this vacuum, the result is catastrophically large. If that energy gravitated in the way the cosmological constant suggests, the universe would have expanded violently from its earliest moments, never forming stars, galaxies, or structure. The observed value of dark energy is staggeringly smaller than this prediction. The mismatch is not a rounding error. It is the largest known discrepancy between theory and observation in all of physics. This has led some to suspect that the cosmological constant, while mathematically convenient, may be conceptually incomplete. From this discomfort emerged alternatives. One class of ideas replaces a static cosmological constant with a dynamic entity, a scalar field permeating space, evolving slowly over time, known broadly as quintessence. Such fields would exert negative pressure similar to dark energy, but with strength that could change as the universe expands. In these models, acceleration is not eternal. It is a phase. Scalar fields are not exotic inventions. They already play a central role in particle physics and cosmology. The Higgs field gives particles mass. Inflationary theory invokes a scalar field to explain the universe's earliest moments. Extending this concept to late-time cosmic acceleration is mathematically natural, if empirically unproven. If dark energy were dynamic rather than constant, it could help explain the Hubble tension. Early universe measurements might reflect a different expansion regime than the one governing the present. Subtle evolution in the field's energy could alter the universe's expansion history without disrupting the well-tested physics of earlier epochs. But such models introduce complexity. They require fine-tuning. They raise new questions about stability and origin. And so, while compelling, they remain speculative. Other approaches turn not to new energy components, but to gravity itself. General relativity has been tested with exquisite precision, but only within certain domains. Solar systems, binary pulsars, gravitational waves. These tests probe strong gravity locally, but they do not fully constrain gravity's behavior across cosmological distances. It is possible, some argue, that gravity behaves slightly differently on the largest scales. Modified gravity theories explore this possibility. Some introduce additional fields that alter how spacetime responds to energy. Others change the geometry of spacetime itself, allowing gravity to weaken or strengthen depending on scale. In these frameworks, acceleration emerges not because space contains a new energy, but because gravity's rules subtly change when stretched across billions of light-years. Such theories must walk a narrow path. They must reproduce the successes of general relativity locally, while deviating just enough globally to explain acceleration and the Hubble tension. Many fail under scrutiny. A few survive, mathematically consistent, but empirically constrained, waiting for decisive tests. Another speculative avenue reaches beyond four-dimensional spaner, in higher dimensional theories inspired by string theory. The universe may contain additional spatial dimensions beyond the familiar three. These dimensions could be compact and hidden, or large, but inaccessible. Gravity, in such scenarios, might leak into these extra dimensions, altering its strength on cosmic scales. Acceleration could be a symptom of geometry unfolding beyond perception. While such ideas are difficult to test directly, they arise naturally in attempts to unify gravity with quantum mechanics. They remind cosmologists that the universe's apparent simplicity may conceal deeper structure. Underlying many of these theories is a unifying question. Is dark energy fundamental or emergent? Some researchers explore the possibility that acceleration arises from the collective behavior of spacetime itself, much as temperature emerges from the motion of particles. In this view, dark energy is not a substance, but a macroscopic effect and expression of deeper, microphysical degrees of freedom not yet understood. This perspective echoes ideas from black hole thermodynamics, where gravity, entropy, and information intersect in unexpected ways. If space-time has an underlying statistical structure, then cosmic acceleration might reflect a tendency towards certain configurations rather than the influence of a new force. The past also casts a long shadow over these debates. Inflationary theory proposes that the universe underwent a brief period of extremely rapid expansion in its earliest fraction of a second. This inflation smoothed space, flattened geometry, and seeded structure through quantum fluctuations stretched to cosmic scales. Inflation is supported by multiple lines of evidence. Though its precise mechanism remains unknown, some theorists wonder whether dark energy is a faint echo of inflation, a relic of early universe physics that never fully disappeared. If the same underlying principles govern both epochs, then acceleration today might be a continuation, not an anomaly. This connection leads naturally to even more speculative terrain. In many inflationary models, inflation does not end everywhere at once. Instead, it continues in different regions, producing a vast ensemble of universes with varying properties, a multiverse. Within this framework, physical constants may differ from one universe to another. Dark energy's value might not be uniquely determined by theory, but selected by circumstance. In such a landscape, the observed value of dark energy would not require a precise explanation. It would be one outcome among many, compatible with the formation of galaxies and observers. Universes with much larger dark energy would expand too quickly to form structure. Universes with negative dark energy might collapse prematurely. Only a narrow range permits complexity. This idea, often associated with the anthropic principle, is controversial. It challenges traditional notions of explanation, replacing inevitability with selection. Yet it arises naturally in certain well-developed theoretical frameworks. It is not a retreat from logic, but a shift in how logic is applied. Still, caution remains essential. Theories of dark energy, modified gravity, and multiverses are not interchangeable speculations. They are mathematically rigorous attempts to reconcile observation with known principles. They are debated, refined, and constrained by data. Many are discarded. A few persist. What unites them is not certainty, but discipline. Each is grounded in equations, not imagination alone. Each makes predictions, however subtle. Each awaits confirmation or falsification through observation. And yet, despite this intellectual richness, no single theory has emerged victorious. Dark energy remains undefined. Gravity remains unmodified. Extra dimensions remain unseen. The multiverse remains hypothetical. This is not failure. It is a reflection of the depth of the problem. The universe is not merely expanding faster. It is challenging the assumption that explanation must be singular and simple. It suggests that reality may permit multiple consistent descriptions, each valid within certain limits. None complete alone. Theories and speculations thus serve a deeper role. They are not answers. They are probes, ways of pressing against the boundaries of understanding to see where resistance forms. In this sense, dark energy has already succeeded in transforming cosmology. It has forced physics to confront its blind spots. It has reopened foundational questions about space, time, and causality. It has reminded humanity that even the most successful theories are provisional maps, not the territory itself. Whether dark energy proves to be a constant, a field, an emergent effect, or a statistical outcome of a larger reality, its presence marks a turning point. The universe is no longer something that can be fully described by what is visible or tangible. It is shaped by what is hidden, subtle, and profoundly unfamiliar. And so the theories continue to multiply as signs of confusion. But as evidence that the universe has not yet revealed its deepest logic, each speculation is a response to a measured fact. Each equation is an attempt to listen more carefully to what the cosmos is saying. The mystery persists not because science has failed, but because it has reached a depth where its answers demand a new way of thinking about reality itself. The mystery did not halt progress. It reshaped it. Faced with a universe that refused to reconcile its own measurements, science did not retreat into abstraction. It responded with instruments larger, quieter, more sensitive than anything built before it, assigned not to confirm comfort, but to interrogate uncertainty. The accelerating universe became not a wall, but a frontier. At the heart of this effort stands a new generation of observatories, each aimed at a different layer of cosmic truth. The James Webb Space Telescope was launched not merely to see farther, but to see deeper in time and structure. With its infrared vision, Webb peers through cosmic dust and into the earliest epochs of galaxy formation. By observing the first stars and galaxies as they emerged from darkness, it helps reconstruct how structure grew under the competing influences of gravity and expansion. Subtle distortions in galaxy shapes, distributions, and ages offer clues about how dark energy began to dominate cosmic evolution. Webb does not measure dark energy directly. Instead, it constrains its effects by revealing how the universe responded to it. Every ancient galaxy mapped, every primordial structure resolved, becomes a data point in a much larger story, one that stretches from the first light to the present acceleration. Alongside Webb, the European Space Agency's Euclid mission was designed with a singular purpose: to map the geometry of the universe with unprecedented precision. Euclid surveys billions of galaxies across a vast fraction of cosmic history, measuring how their shapes are subtly distorted by gravitational lensing. These distortions encode information about the distribution of dark matter and the influence of dark energy over time. By comparing how structure grows at different epochs, Euclid seeks to answer a critical question. Does dark energy behave like a constant, or does its influence change as the universe ages? Even small deviations from a constant behavior would signal new physics, pointing beyond the simplest cosmological models. On Earth, another instrument prepares to join this effort, the Vera C. Rubin Observatory. Unlike space telescopes that focus on deep, narrow fields, Rubin surveys the entire visible sky repeatedly, night after night, over a decade. Its legacy survey of space and time will track the motion, brightness, and distribution of billions of objects, creating a dynamic map of the universe. This continuous monitoring allows Rubin to capture supernova in enormous numbers, refining measurements of cosmic expansion with statistical power never before achieved. Patterns that once relied on dozens of observations will be tested with tens of thousands. Subtle systematics that may have skewed earlier results will be exposed through sheer volume and redundancy. Together, these observatories form a triangulation, space-based and ground-based, deep and wide, early and late, designed to corner the truth of cosmic expansion. Yet perhaps the most profound new tool probing this mystery does not rely on light at all. Gravitational waves ripples in space-time predicted by Einstein, and first detected in 2015, have opened an entirely new channel of observation. When massive objects like neutron stars or black holes collide, they send waves across the universe that carry information about their distance encoded directly in their signal strength. These events act as standard sirens. Unlike traditional distance ladders, they do not depend on intermediate calibrations. Their distances can be measured from first principles, using general relativity alone. When paired with electromagnetic observations that reveal their host galaxies, gravitational waves provide an independent measurement of cosmic expansion. This independence is crucial. If gravitational wave measurements of the Hubble constant agree with late-universe observations, they strengthen the case that the discrepancy is real. If they align with early universe predictions, they suggest hidden biases elsewhere. Either outcome reshapes understanding. The field is young, but its promise is immense. As detectors grow more sensitive and events more frequent, gravitational waves may become one of the most decisive arbiters in the expansion debate. Beyond astronomy, the mystery of dark energy has reached into the domain of particle physics. At its core lies a question about the vacuum, about empty space itself. Quantum field theory predicts that vacuum energy should arise naturally from the structure of fields permeating space. Yet the observed value of dark energy is inexplicably small compared to theoretical expectations. Particle accelerators like the Large Hadron Collider probe this discrepancy indirectly. By studying the behavior of fundamental particles and fields at high energies, physicists search for symmetries or mechanisms that might suppress vacuum energy. Some theories suggest cancellations enforced by unknown principles. Others propose new particles or dimensions that modify how energy gravitates. Experiments searching for dark sectors, hidden particles. Interacting weakly with known matter-seek connections between cosmology and quantum physics. While none have yet revealed a direct link to dark energy, each constraint narrows the landscape of viable theories. In parallel, tabletop experiments test gravity at extremely small scales, probing whether deviations from Newtonian behavior might hint at extra dimensions or new forces. These experiments are delicate, operating at the edge of precision. But they target the same underlying question. Does space-time behave exactly as assumed? Even neutrinos, elusive particles that stream through the universe almost without interaction, play a role. Their masses and behaviors influence cosmic expansion subtly, affecting the growth of structure and the interpretation of early universe data. Experiments measuring neutrino properties feed directly into cosmological models, tightening constraints and refining predictions. What emerges from this global effort is not stagnation, but motion slow, deliberate, and methodical. Science does not approach this mystery expecting a sudden revelation. It advances through convergence, through the accumulation of independent evidence that gradually reshapes the landscape of possibility. Each mission, each experiment, each dataset is designed not to confirm a favored theory, but to stress it. This is how foundational shifts occur, not through spectacle, but through pressure. The tools being deployed are not aimed solely at dark energy. They probe gravity, space-time, quantum fields, and cosmic history simultaneously. The mystery sits at their intersection, where disciplines once considered separate now overlap. Cosmology has become a synthesis of astronomy, particle physics, relativity, and statistics. Its questions are no longer isolated. They demand coherence across scales spanning more than 60 orders of magnitude, from quantum fluctuations to cosmic horizons. Importantly, the ongoing effort recognizes uncertainty as a signal, not a flaw. Disagreement between measurements is treated not as embarrassment, but as information. It reveals where assumptions break, where models oversimplify, where reality resists compression into elegant equations. The universe is not being asked to conform. It is being listened to. This distinction matters. Throughout history, scientific revolutions have followed a pattern. Instruments improve, measurements sharpen, anomalies persist. Eventually, a deeper framework emerges that absorbs the contradictions into a larger coherence. Newtonian mechanics did not fail, it was subsumed by relativity. Classical physics did not collapse, it was extended by quantum theory. The current moment carries a similar tension. Whether the resolution involves dark energy's evolution, modified gravity, new fields, or something not yet imagined, the process underway is the same. Reality is being tested at its seams. And crucially, the search continues without assuming a single outcome. The universe is not obligated to choose the simplest explanation. It is not required to align with aesthetic preference or historical precedent. The tools now in operation, those soon to follow, are designed to confront whatever answer emerges, even if it challenges the deepest intuitions of modern physics. In this sense, science is not stalled at the edge of mystery. It is advancing into it. Every photon captured by a telescope, every ripple recorded by a detector, every particle measured in a collider adds texture to the picture. The universe may not yet be understood, but it is being mapped with a fidelity unimaginable. A generation ago, the accelerating cosmos remains unexplained, but it is no longer unexamined, and as these tools continue to probe the boundaries where calculation breaks down, they do something more profound than collect data. They remind humanity that mystery is not an obstacle to knowledge. It is the engine that drives it forward across centuries. Humanity has carried a quiet confidence that each generation stood closer to the edge of understanding than the last. With every new instrument, every refined equation, There came the belief that the universe was slowly yielding its final secrets. The night sky, once myth and omen, became geometry. Motion became law. Time itself became a coordinate, flowing predictably forward. Again and again, it seemed that the great questions were narrowing, converging toward resolution. And yet history tells a different story. Each time certainty hardened. The universe responded not with confirmation, but with surprise. When Earth was removed from the center of creation, the cosmos grew vast. When Newton's laws appeared complete, relativity revealed time and space to be pliable. When classical physics promised total explanation, quantum mechanics exposed uncertainty at the foundation of reality itself. Each era believed it had reached the threshold of completion only to discover that understanding was not ending, but deepening. The accelerating universe belongs to this lineage of revelation. What began as a precise measurement became a quiet disruption. What appeared to be a technical discrepancy unfolded into a challenge to first principles. The universe did not behave as gravity alone demanded. Space itself seemed restless, expanding with a persistence that no visible matter could explain. And as observations grew sharper, the strangeness did not fade. It intensified. This refusal to conform is not a failure of knowledge. It is a signal of depth. Reality, it seems, is not designed to be fully captured by intuition. It does not arrange itself to be simple at human scales, nor does it reward expectation with obedience. Instead, it reveals itself gradually, often reluctantly, through patterns that only emerge when measured across billions of years in unimaginable distances. The universe is not obligated to make sense on demand. In confronting dark energy, humanity has encountered something profoundly humbling, the realization that most of reality is invisible, intangible, and indifferent to human categories. Stars, galaxies, and life itself, so dominant in experience, constitute only a thin layer atop a far deeper structure. The forces shaping cosmic destiny do not announce themselves with spectacle. They operate quietly, embedded in space, unfolding over epochs far longer than civilization itself. This recognition reshapes the meaning of understanding. For much of scientific history, understanding was linked to control. To know the laws of motion was to predict trajectories. To understand energy was to harness it. Knowledge promised mastery. But the accelerating universe offers no such reassurance. Dark energy cannot be contained. Space-time cannot be commanded. The most powerful influence in the cosmos reveals itself only through its cumulative effect. Beyond direct manipulation or intervention, understanding in this context becomes something else. It becomes an act of listening rather than conquering, of tracing patterns rather than imposing them, of accepting that explanation may arrive without comfort and clarity, without closure. The universe does not yield to force. It yields to patience. There is a quiet dignity in this realization. Humanity is not standing outside the universe, deciphering it like a machine. It is embedded within it, one phenomenon among many, using fragments of reality to understand the whole. The tools of science are extensions of curiosity, not instruments of dominance. They allow the universe to speak in its own language, through light stretched across time, through ripples in space-time, through the subtle imbalance between expectation and observation. In this light, the accelerating universe is not an anomaly to be erased. It is a message. It suggests that reality is layered, that beneath the familiar lies a deeper order, not yet named. That laws once thought final may be approximations, effective descriptions valid within certain regimes but incomplete in others. This does not weaken science. It strengthens it. It affirms that knowledge is not static, but alive. Evolving alongside the universe it seeks to describe, there is also a deeper emotional resonance to this moment. To realize that the universe is stranger than calculated is to confront a limit not of intelligence, but of perspective. Human intuition evolved to navigate survival on a small planet, not to grasp the dynamics of space-time across cosmic history. Expecting reality to align with instinct is a quiet arrogance, one the universe has repeatedly corrected. And yet, despite this indifference, The universe is not hostile. It does not conspire against understanding. It simply unfolds according to principles that are not centered on observers. The same laws that permit acceleration also permit stars, chemistry, complexity, and thought. The same space-time that stretches galaxies apart also carried the light that made awareness possible in the first place. In this sense, indifference is not cruelty. It is freedom. The universe does not owe meaning, but it permits meaning to arise. It does not guarantee comprehension, but it allows inquiry. It does not promise answers, but it leaves traces faint, ancient. It's persistent for those willing to look carefully enough. The accelerating expansion may one day be explained. Dark energy may find its place within a deeper framework, unified with gravity and quantum fields. Or it may remain a boundary, a reminder that not all questions resolve into neat conclusions. Either outcome carries significance. If the mystery is solved, it will likely reveal a universe even more intricate than imagined. If it remains unresolved, it will stand as a permanent horizon and invitation to humility. Built into the fabric of reality, both outcomes are instructive. What matters is not whether the universe becomes fully known, but how humanity responds to what it reveals. The choice lies not between knowledge and ignorance, between arrogance and wonder. The accelerating cosmos does not diminish human achievement. It reframes it. It places discovery within a larger narrative one, where understanding is not an endpoint, but a relationship. A dialogue between observation and meaning, between question and silence. In this dialogue, certainty gives way to curiosity. Control gives way to respect. Explanation gives way to depth. The universe is not a puzzle designed to be solved once and set aside. It is a process unfolding, layered and evolving, inviting attention rather than conquest. Each anomaly is not an error, but a door. Each contradiction is not a failure, but a signal pointing toward richer structure beyond current maps. And so, the final question does not demand an answer. It asks for orientation. If reality is stranger than ever calculated, then perhaps understanding does not mean mastery. Perhaps it means humility, the willingness to accept that the universe is larger than expectation, it's deeper than models, and more patient than any observer within it. The cosmos does not rush to be known. It expands quietly and relentlessly, indifferent to prediction, unconcerned with agreement. It simply is. And in that vast, unfolding silence, humanity listens, still measuring, still questioning, still aware that every discovery carries with it the promise of something stranger waiting beyond, not an end, but an invitation.